Professor Marshall MBE, BSc, DSc, and I can't even pronounce all the rest. He's Emeritus Professor of Ophthalmology at Moorfields Eye Hospital, the University College of London, King's College London. He's one of the world's most distinguished ophthalmic scientists and a pioneer of laser eye surgery, and is renowned for developing laser technologies that have transformed the treatment of retinal diseases and vision correction worldwide. His lifelong contribution to vision research have earned him international recognition and numerous prestigious awards, including an MBE. But perhaps the most important thing that I would like to tell you is that he's one of the kindest and most sincere people that I have ever met, which was at the RI Congress in Helsinki that I attended in 1984, when Professor Shomi Bhattacharya announced that he had identified the first ever gene for X-linked RP. John then pledged his support for our young organization, and now, more than 40 years later, he is still doing so. He was one of the keynote speakers at the RI Congress that we hosted in 1992 in Johannesburg. He's been a founding member of our Scientific and Medical Advisory Board. He toured South Africa giving talks to patients and eye care professionals. His prestige and support influenced the acceptance and legitimacy of our young organization at all levels, South African society. It is my true pleasure to welcome him as our keynote speaker. Thank you, John. The floor is yours.
Thank you, Claudette. I have to say, in my country, the importance of a speaker is inversely proportional to the length of his introduction. And that follows in America, where you get, ladies and gentlemen, the president, and that's it. Okay. Now, for the audience, first of all, I want to reassure you, I'm going to try to keep everything I say in a language that you can understand, because ophthalmologists are known as doctors that use words that other doctors don't understand. But just thank goodness I'm not a dermatologist, because they use words that even they don't understand. So I sympathize with your introduction of saying that there is a problem with the whole linguistics and public speaking, and it's a real issue. And one of the things that I've fought for the last 60 years in my career is getting information across in a form that everybody understands. Okay, so I'd like to begin by taking you back a little. And our RP Association was founded 50 years ago last year. And last year was my 60th anniversary in ophthalmology. Now, when our founder, who unfortunately died quite recently, Linda Cantor, the problem was that if you went to a doctor with RP, he would, first of all, not understand, may never have seen a case before, and would almost certainly say, I'm sorry, there's no treatment or cure. I'm afraid you're going to lose your vision. Now, in contradistinction to this, there were a huge number, I'm talking 50 years ago, of so-called treatments or cures for RP. Now, all of these were fraudulent, and it was quite a variety. For example, you could go to Cuba and have extract of apricots, or you could go to Russia, 2 centers. You could go to Moscow and have NCAD, which was yeast RNA, or you could go to Odessa and have ultrasound. Then you could have hyperbaric oxygen in Italy, a secret treatment that nobody knew anything about in Switzerland. And I'm ashamed to say you could have bee stings in England, because the lady claimed she had special bees which stung you with special stings which treated your RP. So that was the situation 50 years ago. And when I became the initial chairman of the Medical and Scientific Advisory Board, I thought the first thing to do is to review these so-called fake treatments and save people a lot of emotional problems and a lot of money. And together with Alan Leighties from the RP Foundation Fighting Blindness and Alan Bird, we went around visiting these various centres that claimed they had a treatment. Now, it turned out that all these false treatments had the same things in common. First of all, the doctors that had them didn't publish anything. And that's terrible in medicine because we all have to publish to tell all our friends what's going on and why and how. Then the second thing was they all had a little bit of concentration on expenditure. That is, it had to be expensive because you had to feel you were paying for something, but not too expensive because you couldn't afford it and wouldn't go. And then it had to be a little bit painful for you to know that something had been done to you, but not too painful, of course, because you wouldn't go again. Then it had to have multiple components. It had to have exercise, it had to have vitamins, it had to have various tablets, etc., because that makes it very difficult for doctors to test, i.e., which is the important bit of this so-called treatment. And then there were three other things. First of all, it had to be repetitive. You had to keep going back to the doctor. And the reason why it was repetitive was because the doctors needed a way to blame you, i.e., if only you had come back for the 100th time, you'd have been okay. But the fact you didn't, it's your fault, not my fault. And then it had to be, you had to give up something. That is, if you smoked, you had to stop smoking. If you drank, you had to stop drinking. If you love your wife, you had to stop loving your wife. Because again, I've got to be able to blame it on you. It's not my fault it doesn't work, it's your fault. And the most important thing about all of these was it had to be in another country because your doctors told you that it wasn't treatable. And that was really a big, big problem. Okay, so having settled that, we upset the press and we upset lots of our members. But in reality, they rapidly came to the conclusion that it was much better to have the truth than these fairy stories that were being promulgated. So, where did we go from there? Well, the first thing we decided was when RPs get together, they all have a different disease. You know, you sit there and said, "Oh, that's not what happened to me." "Oh, no, that's not." "Are you sure you've got RP?" It's just not like that. Well, of course, there are lots of different types of RP. We now know there are lots and lots of genes, which I'll talk about in a moment. But at the time, all we really knew was that there were three familial types. That is, there seemed to be a form which occurred in generations, regardless of sex, from generation to generation. And that was the so-called dominant disease. And then we knew there were a large group, a very large group, in which there was no previous history, but suddenly it crops up. And then that was the so-called recessive, where we needed a genetic defect in both father and mother who were carriers but had no symptoms. But in terms of their children that had two defects inherited, they showed so-called recessive disease. And then there was another form that went from mothers to sons, so-called X-linked disease. So we knew there were these three different types. And the first thing we did was to say, well, how does the disease progress in these three different types? Now, I'm going to give you a big generalization and say that on the whole, autosomal dominant, that is the one that occurs generation to generation, is a relatively mild form of RP. Yes, it can lead to total loss of vision, but it tends to occur late in life and move quite slowly. By contrast, those individuals that have the recessive form tended to be quite aggressive, occurring in the young and moving quite quickly to significant visual loss. And the same thing happened with X-linked disease. So what did we do? Well, we tried to break down all the different types of RP, i.e. the three different groups, but the different processes. And this was called defining the phenotype. What does that mean? It just means looking at how individuals lose their vision. Okay, so we spent a lot of money on that, and we pulled together lots of different scientists using different techniques, electrophysiology, where they put electrodes on your eye, flashing lights, where they look at the effect of light loss, and all sorts of things, which begun to give us an understanding of why there were so many different appearances of RP in the RP clinic. Okay, so just a very superficial beginning understanding. But did that take us anywhere? Yes, because having got a somewhat more refined grouping, we went from what we originally called and please forgive me, this is no reflection on individuals, but in medicine it was called a dustbin diagnosis. If you didn't know what was going on, you put them in the bin. And that meant that it was a bit like a man limping. You could say, oh, he's got a limp. But he may limp because he's broken his ankle. He may limp because his shoes are too tight, or he may limp because he's got a stone in his shoe. Now, it's no good giving a pair of new shoes to someone with a broken ankle. So, by doing this study and beginning to break down RP sufferers, we knew that we had to be much more specific in terms of how to treat them and how to treat them in the future. And that led to a huge amount of investment in studying the cells of the retina in RP, but also studying the genetics in a more sophisticated way. And that was the beginning of molecular biology and looking for specific genes within the RP group. Now, again, we had some spectacular early successes, and one of these was in guide dogs. Now, unfortunately, Labradors and Retrievers, which are often used as guide dogs, have a form of RP. In fact, they have two forms. One is like a macular degeneration, and one is more like RP. And by looking at the genetics of the dogs, we were able, at quite an early stage, to get with the work of Gus Aguirre in Philadelphia, to find specific genes in dogs. And there was a spectacular video of a dog called Lancelot. I never saw Guinevere, but I did see a lot of Lancelot. And Lancelot was treated and could actually catch frisbees. Now, before the treatment, he wouldn't even have seen the frisbee, let alone be able to catch it. So that was an indication that by finding specific genes, there was the potential downstream for treatment. And we saw the switch from dogs to man, as Claudette has already said, with the work of Shomi Bhattacharya, who found the first RP gene, which was an X-linked gene. And that really was a wildfire, because finding the first gene meant we rapidly went on to establish worldwide many so-called gene hunters who spent their time going through the chromosomes of RP sufferers and finding specific genes. Now, the gene hunters were followed by the protein chemists, because once you know what the gene is, you need to know why that goes wrong in the cell, why the chemistry goes wrong, and how that causes visual loss. So the gene hunters and the protein chemists led to some very early types of gene therapy. And I know Claudette's going to talk about that, so I'm not going to spend too much time on that. But basically, we saw an FDA approved gene therapy for RP65. And that really came out of the work of you guys sitting there convincing doctors that they couldn't just ignore you. They had to put more effort into inherited retinal dystrophies. And that is fantastic, the work of individual countries and grouping together with the International RP Association. Okay, so where's gene therapy today? Well, gene therapy today, just the basics. There are really three types. The first type is the RP65 type, where you say, okay, this is a recessive disease with two bad chromosomes. So if I put in some normal genetic material, hopefully I can overcome that effect. And that's what's called gene addition or gene augmentation. Now, more recently, a few years ago, there was a significant discovery of an enzyme in a sea animal called CRISPR, and that enabled us to cut the DNA spiral specifically, so we could cut out defective genes. And that's called gene editing, where you cut out genes that you don't want. And that's going to be useful in autosomal dominant diseases, whereas the addition is really good for recessive diseases. But even more recently, we've had something called gene silencing. So now we have a group of studies whereby we can switch off the bad signal between the chromosome and the manufacturing sites in the cell. And that's a messenger RNA. If we switch that off, and we have to switch it off time and time again, that's going to be a group of treatments in which you have perhaps drops 3 times a week. But gene silencing has a huge amount of promise, and again is in the process of being set up for proper clinical trials. So I have to say to you, you're living in a very exciting time. Now, there's another element of genes, and that is different genes operate at different times during our lifetime. If you think about it, when we're in the womb, there are a whole number of genes called homobox genes, which really only work during embryogenesis, in which they cause things to develop, i.e., they cause the eye to develop, they cause the brain to develop. In the eye, they cause the light sensitive cells to develop. Now, these genes, which we can simply call clock genes, switch on and off. And we're beginning to understand how to switch these clock genes on and off. Now, I want to give you an example for a moment. If you think of rods and cones, rods, I've always sort of thought of the business element is the so-called outer segment, which is like a giant packet of biscuits. You've got about 130 million rods in each eye during your early childhood. And in each rod, there are about 1,000 discs in their packet of biscuits. Now, that's not stable, because what happens is every day you make about 30 new biscuits. They progressively get displaced down. And then every morning when you first open your eyes, the retinal pigment epithelium bites the end off all your rods. So those of you that have had a bad morning, perhaps due to alcohol, you can now blame it on your rods. It's being bitten off when you wake up. Okay. Now that process works very well for most individuals throughout their entire lives. It slows down a little bit as we get older, but in RP, in many forms of RP, the rod outer segment, i.e. the packet of biscuits, gets shorter and shorter and shorter and shorter until it can no longer respond to light. And the rod dies. Now, with cones, it's a similar process, except you shed your cones when you go to sleep, believe it or not. And when cones lose their outer segment, they hibernate. So you've got all the connections of those cones back to your brain, but no sensation of light because it's lost its outer segment. So people are beginning to look at, can we play with clock genes? For example, we've got all the cone cell there. Can we switch on the process for it to make discs at a time in life when it normally doesn't make discs? Now, that sounds absolutely crazy, but if you look at the animal kingdom, lizards, they lose their tail, they can grow a new one. You pull their arm off, they can grow a new one. And that's clock genes. And when when evolution does something that's good, it tends to keep it. And so we now need to say how many of these clock genes are still there and how difficult is it to activate them. And there's been some very interesting work in France and now in the States, and hopefully soon in the UK, which will be activating clock genes. And just as two more examples, a lot of work on zebrafish, which have this capacity to play with their clock genes. And more recently, we've discovered some snails which can completely grow a new eye. So that's opened up a number of new genetic areas of research. Okay, so moving on, you've probably heard of stem cells, and stem cells were great. We're putting stem cells into the eye, mainly retinal pigment epithelial cells. But the handicap in the early days was embryology, and we could only really do it with embryonic tissue. Now, with modern research, we can transform skin cells into eye cells. Great. And then use those as a body to implant to give us stem cell implantation. And there is also some work on animal tissue to do the same thing. Okay, so in the front of the eye world, we're already using material from pig eyes transplanted into human eyes very successfully. So I'm trying to give you a flavor of the excitement that someone like me is experiencing in over the last 6 years. It's all moving. I just want to end up with two last things, optogenetics, where people are trying to put in light sensitive material into the retina, because if you look at the RP population, genes and gene manipulation is going to be great for the next generation. But lots of you have lost vision, you've lost photoreceptor cells. What can we do for you? Well, regeneration, revival is the key. And one of the areas is to put photoactive pigments into cells that are still there. So initially, the photoactive pigments have gone into glial cells, the sort of structural cells of the retina. Some has gone into two different types of neurons, but really we want to target cells called bipolar cells because they have a much better connectivity between the brain and the eye. And as well as these photosensitive pigments, we have things called microdots, which are incredibly small electronic components which flash when light is shone on them. And there is a group at King's College in London that's looking at the use of microdots for replacing visual sensation. And finally, bionic eyes. Well, you've all heard about bionic eyes. They had a bad start with wiring problems from front to back. They had problems with camera, but now it's all done almost on the web. And it again is having a resurgence. And Elon Musk, yes, Elon Musk, he's got some cortical implants in the brain, which he is hoping will actually lead to replacement of lots of function, including paralysis and loss of vision. So my take-home message to you all is there's a huge amount going on out there all over the world. It's been activated by patients like yourselves, and you need to keep kicking doctors to remind them that you're still here. And well, all this gene stuff is terrific, but what about me? I need to see. It's happening. It's beginning to happen. And recently, the RP Foundation in UK has funded some new work from Robin Alley's group to look at putting very clearly modified cone cells into human retina and starting a clinical trial. I'd like to thank you for the opportunity to speak to you. I hope I haven't bored you to twitters. I hope I haven't used too many long words. In the annual general meeting of the UK Society, I ran a competition each year for children that were there and bored out of their mind. And they got £5 for the child that found the longest word that I and other scientists had used. Thank you.
Any questions for Professor Marshall? So much thanks from my side, Professor Marshall. I think you make it so accessible, the study of the retina. And I know all of us here, we are all experts in our own condition, but it's wonderful to hear from a pioneer, a person that has actually started out in this field and knows so much about everything. So the floor is now open for questions. We can ask 3 questions from the people on the floor and 2 from people online.
No questions, great.
Questions so easy, not so easy.
It's not going to happen, Prof.
To start by asking you a question that we are asked every day. And I know my answer to this is probably between 10 and 20 years. But people often ask, what about stem cells?
Well, stem cells are moving apace, and as I said to you, they've now reached a point where there are clinical trials. Initially, there were quite extensive trials at Moorfields under Pete Coffey, who unfortunately died recently, using pigment epithelial cells. But I think it's really much more exciting that we're now beginning to see photoreceptor cell transplants. It works reasonably well in dogs, and we're hoping it will work reasonably well in humans. The big issue with all these trials is not the scientists who have brilliant ideas and run away, etc. It's the bureaucracy of getting approval to start. And that's been the biggest issue. I mean, my idea for changing the shape of the eye using lasers took 10.5 years for the American Food and Drug Administration to give approval. 10.5 years. And it cost $23 million to get that approval. So for me, FDA stands for funereal data analysis.
That's very good. Thank you. Have we got any questions in the room for Professor Marshall?
Yes, we do. Yes. Hello, hi. Professor, this is a question that I'd like you to please answer. What is your professional medical opinion regarding preventative steps for narrow angle glaucoma for patients with RP, recessive RP?
Oh,
That's number one. And number two, the optogenetics that you spoke about, are there any timelines involved in terms of clinical trials? And if we are interested in getting involved, what's the procedure? Thank you.
okay. Two questions. First of all, the glaucoma issue. Well, I should say that glaucoma to me is the Rip Van Winkle of ophthalmology. You can go to sleep for 100 years and then wake up and think, oh, yes, the same drops, etc., etc., etc. That changed, and it changed quite dramatically with a laser treatment called SLT. So now at Moorfields, the first line of defense in many cases of glaucoma is SLT treatment before drops. So it really depends what's causing it in RP and how that relates to the whole glaucoma issue. But glaucoma is moving apace. Now, you sort of link two things together there, glaucoma and optogenetics. And the big issue that we found, even in the UK, which is a relatively small geographic country, is to get people genetically diagnosed, i.e., what particular gene do you have and which particular treatment protocol will help you. So that's the first big issue, to get to see the right doctor for the right treatment at the right time. And then the second issue is, can you get in a pilot study or early clinical trial? And there are already pilot studies and early clinical trials on optogenetic treatment regimes. They're already happening. But it's a question of selectivity. And I don't know the current situation in South Africa as to how many genetic clinics you have for RP and how easy it is to get diagnosed. But that's the first issue. And then the second issue is, how do you know about these various treatments? Well, you need to follow, I'm sure your website's going to be a really active site, but the various publications of the various international RP societies. And sometimes there is a sort of international appeal because there are just too few patients in a given area. So it's very difficult to answer your question absolutely specifically, but I hope I've given you some food for thought.
Thank you very much, John. Is there anybody else in the room?
Yes, we have one more here.
Morning. So my question is related to cone rod dystrophy. I just wanted to ask, since we were focusing on RP, can you please also explain any new updates regarding like gene therapy for patients with CRT? Can you please also just inform, like I said, any new updates for patients with CRT? And also, where in the world are we right now with like looking for cures or the prolongment of the disorder? Thank you.
Okay, I'm going to speak specifically about cone rod dystrophy in my presentation, John. So
Okay.
if you had something other, generic to add, but I'm going to talk specifically about clinical trials for cone rod.
Okay, I'll leave it to you.
Thank you. I think now we have one more in the room.
Good morning, Professor. My question relates specifically to where we stand with Stargardt's treatment, specifically for Stargardt's autosomal recessively inherited Stargardt's.
Okay, I'm speaking about that as well in my talk quite extensively.
Okay.
Thanks.
There's a lot of work going on there, particularly with Robert McLaren in Oxford in this country. So yeah, it's not one of the orphans of RP. It's really one that has received a lot of investment and a lot of interesting treatment, which I'm sure Claudette will cover.
Thanks. Thank you, John. Have we got anything else online? We can take one more question online, and that's it. That's the last question.
Okay,
Yeah, I
I'm
think-
going to read the question from the group. It says, with recent developments in AI, have you seen an increase in cures for all IRDs, or are most treatments aimed at curing RP?
That's up to you.
Yeah, I have to say I have a vested interest here because I've only recently been involved in uh, selling off an AI company. AI has just been absolutely astounding because initially we used it to do what doctors do, i.e., for example, in diabetic retinopathy, we told the computer, this is how doctors diagnose diabetic retinopathy. Can you do better? And that was interesting. On the whole, it could do slightly better. But what became very interesting was when we just put the images in and said, what do you make of this? Well, the first thing it did from just looking in the eye was to tell us the sex of the eye, which I found extraordinary. The next thing it did was to differentiate between your chronological age, i.e., your birthdays, and your biological age, i.e., the aging sequence in your eye. So it could say, okay, your birthday, you're 68, but you're doing very well because chronologically the cells in your eye are only 50, or vice versa. But then it went one step further and said, well, not only can we tell your biological age and from your chronological age, we can tell you when you're going to have a severe cardiovascular event, a stroke or a heart attack, and the time base. So that was astounding, and that took us almost 3.5 years to understand how the computer did that. So AI is moving at a pace together with, and I didn't mention this and no one will have, but quantum computers that do these things so much quicker. It's going to have an impact. It's going to have its initial impact in diagnosis, but already we have another group which AI is determining treatment, i.e., when to treat, how frequently to treat, etc., etc. So yes, AI is something to watch. Um, and it's very interesting to see how clinicians are reacting because I said to Alan Bird, very famous in this area, Alan, how many patients do you think you've seen in your lifetime? And he said, well, I don't know, somewhere between 10 and 20,000. And I said, how many do you remember? He said, oh, probably 100. And I said, how many of those are failures and how many are successes? And he went, oh, 90% were my failures because they haunt me. And the successes I never see again. And AI is revolutionizing that group. So the diagnosticians are under real threat. Am I going to be replaced totally? And just recently, in fact, in a journal I received yesterday, it described the first fully automatic AI controlled cataract extraction with no surgeon involved. So it's now it's moving from diagnosis to robotics and surgery. I'm sorry to be so dynamic. It's probably very disturbing, those of you that can see things, but I get so enthusiastic still. And thank you for some interesting questions.
Thank you so much, John. And as always, we are indebted to your enthusiasm and your support. Thank you very much.